Welcome to the subject operating systems. Today we are looking at the chapter titled Deadlocks. All the presentation material is based on the textbook that is indicated in the syllabus. The core topics for discussion: system model, deadlock characterization, methods for handling deadlocks, deadlock prevention, deadlock avoidance, deadlock detection, recovery from deadlock. The concern in operating systems is the fact that there are limited resources in terms of memory, in terms of input output devices, in terms of the way we share the screen, the computer screen, multi users, multitasks. All these will have to share the available resources, and the functionalities of the operating systems include the management of all these resources in a manner where we have good response time, less waiting time, we have a very good throughput, and overall we will have a user satisfaction that makes users go back to the system to do more and more work. In these circumstances, what we find is there is always a possibility that many users, many tasks are contending for a limited number of resources, and it is quite possible that some resources are in demand, and if these resources are not given back to the processes, it appears that the system is always running but no work is getting done. That situation in an operating system is called deadlock. Now, if we look at the way in which we are modeling the operating system managing the resources, we find that we need to have a description of deadlocks which prevent sets of concurrent processes from completing their tasks. As I said, the resources are available, but all resources necessary for any given process is not there. They are not available for the process to complete. So, in theory the system is always active and running, but there is no process that is completing its task because at least one resource that it needs to complete the task is held by some other process, and the system is not able to give that resource to the process. Limited number of resources, multiple processes, multitasks, multiple users. It's all the case of ensuring that the system gives very good response time to all, minimizes the waiting time, but this condition is very special, and that's the reason why we need to describe what is called deadlock very carefully. To present a number of different methods for preventing or avoiding deadlocks in a computer system. A system consists of resources. It's not completely out of context to think of operating systems primarily as a resource manager. As I said, limited memory, limited input output devices, limited CPU time, limited CPU cycles. These are typical resources which can be called R1, R2, R3. We name a resource, give it a notation which tells that it's resource 1. Each resource type Ri has Wi instances. It's quite possible that there may be multiple resources of the same type. R1 is a type of the resource. In this type of the resource there are multiple. For example, here I am seeing 3 screens, 3 computer screens, one ahead of me, one right in front of me where I see and read, one to cross check by my side. There are 3 computer screens out here. The resource type is a monitor. There are 3 instances of the monitor as I am doing this lecture. Each process utilizes a resource as follows: it requests for a resource, it uses the resource, it releases the resource. So, these are the 3 dominant activities which every process, either it is belonging to a single user or multiple users initiating multiple processes, has 3 activities to do: request for a resource, use a resource, release the resource. To whom do they request? To the operating systems. Deadlocks is thus a very important criteria to check in the design of an operating system. The concern in deadlocks is once there is a deadlock, we won't know what is happening and we need to make a special effort to detect the deadlock. So instead of waiting for a deadlock to happen and then go ahead and then see whether it has been removed or not, we like to have algorithms which either avoid a deadlock or prevent a deadlock. So the system model is very clear. All resources are categorized as types R1, R2, R3. If there are multiple instances of the same resource, we will use a notation Wi. So for example, monitor is Ri, M1, M2, M3. 3 monitors are the instances of the same resource R1. Each process utilizes a resource as follows: request, use and release. Deadlock can arise if 4 conditions hold simultaneously. System specialists, systems theorists have had a fantastic study done on the way in which the system manages all the resources and the multiple instance of all resource types, and we realized that deadlock will arise when these four conditions hold simultaneously. One is mutual exclusion. Only one process at a time can use a resource. If one process is used, for example, the chair I am sitting, only one person can sit in the chair. Even if multiple persons are there in the room, only I can use the chair. Hold and wait, holding some resources, waiting for some other resources requested or held being used by another process. The third condition is no preemption. Once a resource has been sought by a process, until the process has completed its task using the resource, it cannot release the resource. Circular wait. The processes are all holding some resources, waiting for some other process to release some resources. There is obviously a chain of waiting of these processes. P0 process waits for P1, P1 waits for P2, and if each one forms, if this sequence of waiting forms a circle or it has a cycle, there is a possibility of deadlock. So deadlock can arise if 4 conditions hold simultaneously. I repeat: mutual exclusion, hold and wait, no preemption and circular wait. Deadlocks can occur via system calls, locking. In the databases we lock some records. There are many ways where we think a deadlock can occur, and the task of the operating system is to ensure that there is a way in which you anticipate a potential deadlock, avoid the deadlock, prevent the deadlock, or when a deadlock has occurred, it should know how to detect. So a set of vertices V and a set of edges E. This is what is called a resource allocation graph. It's something like a notebook which the operating system maintains. It has the processes, it has the resources. So what is it making note of? A process P1 has made a request for R1, a resource type R1. A process PM has made a request for a resource type RM. It's a kind of a register where you are reserving the resources. U is here a process. A process is triggered by a user. A user can have multiple processes, many users can have many other processes. Every process P1 has made a request, made a reservation request. This is what we have been talking about. In the earlier slide, there are 3 activities. It has indicated, a process has indicated that it will want to use this resource. If the process is very clear that it uses the resource from this point in time to this point in time, there is nothing like it, like what we have been doing in reserving the normal resources like this room, this studio. The studio is reserved for this lesson now. There is a register. My colleagues here have made sure that this studio is available. Nobody else is using this studio now. Used it, released it, we blocked it for some time, we release it. This is not easily possible when we are talking about software processes asking for resources, but that is how we maintain the resource allocation graph. A process P1 has made a reservation for R1. a process P2 has made a reservation for Rm, a process Pn has made a reservation for R2. If there are multiple instances, like I said, 3 monitor, the type of the resource is monitor, but there are 3 instances, we follow a different notation. So a set of vertices will have a request edge, that is P1 has requested for some resource Pi has requested Ri, and it will tell that assignment edge is a directed edge, Ri has been assigned to Pi, it has a different notation. So next we talk about a resource allocation graph. A process is a circle, resource type R1 with 4 instances. This has 4 instances. P1 requests instance Ri, it is like this. P1 wanted Ri, it is an arrow between the process P1 and a resource. Pi is holding the resource is now with P1. If it is in this direction, it is a request. If it is in this direction, it is holding, it has been allocated. This is a simple notation for what we call a resource allocation graph. Request edge is in this direction, assignment edge is in the other direction. P1 requested resource, R1 is allocated to P1. So we can now find a way of having our reservation register in the form of a graph. Graph theoretic algorithms are very nice to analyze. We will see in the due course of this lecture how the algorithm looks. But right now, this is an example of a resource allocation graph where P1 asked for R1, R1 is assigned to P2. P2 has asked for R3, R3 is assigned to P3. There are 2 instances of R2, one is assigned to P1, the other one is assigned to P2. R4 is a resource, there are 3 instances, none of the processes P1, P2, P3 need R4 here. This is how an example resource allocation graph is. With the deadlock, it is easy to understand that P1 is waiting for P1 got R1, R1 is given to P2, P2 is wanting R3, R3 is given to P3, P3 wanted R2 but is not available. So there is clearly a reason to believe that there is a cycle. None of the processes P1, P2, P3 can individually complete their task, but the system keeps on telling that P1 is waiting for something, P2 is waiting for something, P3 is waiting for something. Once that waiting is over, we will be able to finish. None of them will be able to finish. So it is always busy doing nothing. A deadlock has occurred. It's very easy to see that a cycle here is very clear, and that cycle is easy to detect if the representation of your reservation register, booking register, is in the form of a resource allocation graph. Graph with a cycle but no deadlock. It is also possible that in theory there is a cycle, but then it is all possible because of another process completing, it will release the cycle, it will break the cycle. Only if there is a cycle, there is a deadlock. Cycle can be there, but there need not be a deadlock if there is a possibility of another process taking away the resource. If graph contains no cycles, no deadlock. If graph contains a cycle, if only one instance per resource type, then deadlock. If several instances per resource type, possibility of a deadlock. So what we have been talking about is to understand that once we maintain the reservation register or a booking register for resource, we can understand from the representation of that booking request before all processes start executing the book. Once we understand that as a resource allocation graph and use the graph theoretic algorithms, irrespective of the number of processes, irrespective of the number of types of resources and the number of instances, we will ensure that we will either prevent a deadlock or avoid a deadlock, or when a deadlock occurred, then we will detect it and then we can always recover. Ensure that the system will never enter a deadlock state by either making sure that at the time of granting the request to a process. Allocating a resource, we will make sure that it is not going to form a cycle and then allocate. Deadlock avoidance, and then we talk about if there is a deadlock state, we will allow it to get into a deadlock state and recover. Ignore the problem and pretend that deadlocks never occur in the system, used by most operating systems including Unix. In Unix, it is very difficult to have a deadlock condition. There is a case study which I will do later in this set of lectures, where we will talk about why Unix designers are very confident that there is no deadlock. Restrain the ways requests can be made. We ensure that every process makes a request only if there is a condition on mutual exclusion. Not required for shareable resources, must hold for non-shareable resources. If the resource is readily shareable, that is, we talk about resources which are what is called multiple processes can always use that resource. Say for example, we talk about the way in which we are using a road. There is the road to this particular studio is used by all. It is shareable resource. There is no reason to believe that it should be blocked for me, whereas the studio is blocked for me. There is no reason to believe that the road need to be blocked. It's read only. Many people can use. If it is a non-shareable resource like this, then yes, we need to be worried about mutual exclusion possible. So we mark the resource type as some resources are shareable, some resources are not shareable. Hold and wait must guarantee that whenever a process requests a resource, it does not hold any other resources. Now these are ways in which we are becoming a little more conservative in making the request. Deadlock prevention algorithms place conditions on the process before asking. Before asking, the process must ensure that is the resource shareable or not shareable. If it is shareable, it can go ahead. If it is not shareable, it should wait for somebody to tell that yes, now it is shareable, you can go ahead and use. It needs a confirmation saying that the resource is allocated if it is a non-shareable resource. Hold and wait, once again we are placing conditions on the process when it is requesting the resource. We are preventing it by saying that it is a very disciplined way in which the processes ask or request for resources. It does not hold any other resource, but then it is asking for one more resource. Require process to request and be allocated all its resource before it begins execution, or allow processes to request resources only when the process has none allocated to it. So the point is, much before it begins the execution, it will wait until all resources are allocated and then it begins execution. Now in this case, maybe it is always true that we will be having a suboptimal resource utilization, because it has to wait. I have everything except a pen on hand. I will have to wait until the pen happens to write something. It can happen in these cases that the resource utilization is low, it is holding 5 out of 6 resources that are necessary, the 6th one is taking lot of time to come, and unless it comes, the process cannot complete. Starvation, it is eternally waiting for resources and nobody is giving any resource, because it has to make sure that it gets either all or none. If a process that is holding some resources requests another resource that cannot be immediately allocated to that, then all resources currently being held are released. Even if one resource cannot be given, it will release all resources that are being held. Preempted resources are added to the list of resources for which the process is waiting. Process can be restarted only when it regains all old resources as well as new ones that it is requesting. So the condition here we are putting on the process request is, 1, it should check whether the resource type is shareable or not shareable. Second, either it gets all the necessary resources or it does not do anything until all resources are with it. It will release all resources until it gets all the necessary resources. Impose a total ordering of all resource types and require that each process requests resources in an increasing order of enumeration. How do we prevent that one is not waiting for the other? If a process number is higher, let us say order of enumeration is higher, give it the priority. Low priority things will automatically go. A circular wait can be avoided. All this is possible because we have begun to represent the way the resources are reserved using what is called a resource allocation graph. So this is a code. You can take a look at this code, and what we will understand from this code is we can easily understand that there is one thread that is running in this function, thread 2 runs in this function, and we have a way of working on these two. You get one lock before transaction 1 and 2 are executed concurrently. Transaction 1 transfers $25 from account A to B, and transaction 2 transfers $50 from account B to account A. So whenever the account A is being accessed, nothing else is accessing account A. It is locked. It is locked before anything happens. Only after the entire transaction with account A is complete, it is unlocked. Whoever gets to that transaction first will go ahead with that transaction. Now what is happening is that we need to be very clear that the way we are making sure that the account is very clearly accessed by exactly one process is monitored by the system, and whenever we want, it's a bank account that we are talking about, and we'll have exactly one operation, transaction 1 and is only doing first, transaction 2 will do next. The lock ordering, first you finish transaction 1, next you finish transaction 2. In theory, transaction 1 and transaction 2 can happen simultaneously, but what we are doing by having a good resource allocation graph is that at the time of updating the account, it is first transaction 1, next it is transaction 2. They are serialized by using what are called locks. The code is there in this. First you put one lock, second you put another lock. Only after one lock is released, another lock can be used. So by using locks and ordering the locks, we are making sure that where there is a potential deadlock possible, we serialize. It is called a transaction serialization. Deadlock avoidance requires that the system has some additional a priori information available. Now what we have done earlier on is, on the line we don't know which process requires what resource type, how many instances of that resource. This is what we called in deadlock prevention. Whereas in deadlock avoidance, we know before. The simplest and the most useful model requires that each process declare maximum number of resources. Right at the beginning, every process will tell, I want this many instances of these resources. So before the process is run, we will do this resource allocation completely in a static mode and find out how we can easily avoid the deadlock. So if a process can predict the resources correctly, there is nothing like the deadlock avoidance, but that's very difficult because we do not really know the exact context in which the process executes. The compile time tells this many resources are necessary, but depending on the input, depending on the context in which the process is getting executed, we may not be sure whether all those resources are necessary or it needs more resources. So it is something like making sure that we are going well prepared for the examination without knowing any questions, and we go and write with an open mind, or we get prepared saying that these are the potential questions that can come, and we are a little more clear as to how to write the examination. These are the ways in which we are talking about. When a process requests an available resource, system must decide if immediate allocation leaves the system in a safe state. What is a safe state? The safe state is going to be like this. I'll come back to that. The safe state is like this. There is no deadlock visible. So this is the way in which we make sure that the entire resource allocation graph speaks whether there is a safe state. If there exists a sequence P1, P2, Pn of all the processes in the system, such that for each process the resources that P1 can still request can be satisfied, by currently available resources plus resources held by all the Pi within j less than L. If P1 resource needs are not immediately available, P1 can wait until Pj has finished. All this is nicely represented in a manner where if a system is in the safe state, there is no deadlock. If a system is in unsafe state, there is a possibility of deadlock. We can avoid by ensuring that the system will never enter an unsafe state. If you can find out what is a safe state like this, what is an unsafe state, then we can fix the deadlocks happening only when the system is moving into unsafe state. Is it possible? The answer is yes, because we have fantastic graph theoretic algorithms that will help us do this, and an algorithm which is very specifically telling us where to draw a line between safe and unsafe state is what is called the Banker's algorithm. Single instance of a resource type, use a resource allocation graph, use the Banker's algorithm for multiple instances of a resource type. So we have a simple way of using a resource allocation graph if there is only one instance of one resource type. If it is a multiple instances of a typical resource type, we use Banker's algorithm. So this is enough. The first one is very clear. It's a graph theoretic algorithm. You can simply look at the graph, and by inspection, by the analysis of a graph algorithm, you can find out whether there is a safe state to proceed or we are entering the unsafe state, and there is a small but there is a non-zero probability that a deadlock can occur. So we have to find out if it is a single instance, we can come up with this safe state. When we are entering the unsafe state using the graph theoretic algorithm, we are entering the zone where there is definitive possibility of a deadlock can happen. As we come close to this position where the deadlock is going to occur, we would like to avoid things and come back to the safe state. Even though it may mean a suboptimal utilization of the resources, it is still worthwhile because a deadlock is going to be more expensive than the suboptimal utilization of the resources. Deadlock will simply tell the entire process is busy but nothing else is happening. It appears busy but nothing else is happening. So we talk about Banker's algorithm. Claim edge P1 indicates Pj. This is all the way in which it is represented. An unsafe state in a resource allocation algorithm, multiple instances. Each process must a priori claim maximum use. When a process requests a resource, it may have to wait. So data structures are available. We can talk about it in a complete matrix form. This is the safety algorithm. You can read it up in the textbook. Resource request algorithm for process Pi. The notation is clear. The way in which this code is executed is also here. 5 processes, 3 resource types. The previous slides, all of them will give you a notation. At a given snapshot, you can draw the resource allocation graph, and from that you can have deadlock prevention, deadlock avoidance, and also deadlock detection. So single instance of each resource type is very easy. Resource allocation graph and a wait for graph. Resource allocation is here. Some resources are allocated, processes are waiting for some other resources to happen. There are multiple instances of a resource type. It is available, it is allocated, or there is a request. This is a detection algorithm. It tells you whether there is a deadlock that is already there, and we can recover. So using the same algorithms, same notation, we can find out whether there is a way in which the deadlock is anticipatable, deadlock is preventable, deadlock is avoidable, or a deadlock can be detected. If detection algorithm is invoked arbitrarily, there may be many cycles in the resource graph, and so we could not be able to tell which of the many deadlock processes caused the deadlock. The cause of the deadlock can also be found out, and we can release the resources through an explicit intervention of a system call. We can abort all deadlock process or abort a chosen process at any given time until the deadlock cycle is eliminated. So we have a way in which we can abort priority of the process, how long which process should be aborted so that the deadlock state will not be there. We can release the resources. It is a question of understanding the resource allocation graph based on the notation that has been discussed and the algorithm that we have been using, how long the process has computed, resources the process has used, resources process needs to complete, how many processes will need to be terminated, is process interactive or branch. One good aspect of deadlock is the resource allocation graph will tell us precisely whenever the deadlock has occurred answers to all these points, and then we will decide which of the processes can be aborted, which is the victim, minimized cost, rollback, starvation. And in summary, I would simply tell that there are ways and means of modeling the operating system as a set of resources. A graph, resource allocation graph, can be drawn, and studying the resource allocation graph we can come up with algorithms for deadlock prevention, deadlock avoidance, deadlock detection. And once the deadlock is detected, the way in which the resource allocation graph is represented will tell us which is the way in which we should abort a process, which is the way in which we should take away the resource process needs to complete. So we can select a victim, we can either roll back to a safe state or starvation. In essence, the way in which all this system model works is it will tell us very clearly the idea of what is called a safe state and an unsafe state. By using a model like this, resources, resource types, instances of a given resource, we are able to understand that this is how a resource allocation graph looks, and from this, using the algorithms, we will arrive at what is called a safe state and an unsafe state and a potential deadlock. That's all is the exercise that we need to do in this particular chapter called deadlocks. And what is our goal? Our goal in this chapter is to convert the entire system, processes and resources into a resource allocation graph, use the graph theoretic algorithms if there is a single instance. If there are multiple instances, use an algorithm called Banker's algorithm and come up with what is called a maximum safe state, unsafe state, deadlock state. By being conservative about allocating the resources, we understand how to avoid the deadlock and unsafe states and always operate the system in the safe state. Thank you very much.